Welcome to your Flight Controls Cram Session Explainer. Look, if you're gearing up for your private pilot ground exam, you're in the exact right place. We're skipping the fluff and jumping straight into the core aerodynamics and mechanical systems you absolutely need to know to pass with flying colors. Let's do this.
Here's what we're tackling today: the holy trinity of axes, roll and adverse yaw, pitch perfect, and finally, yaw and V-tails. Starting off with Part 1, the holy trinity of axes. We're looking at control surfaces, axis of rotation, and stability.
Okay, I want you to take a mental screenshot of this right now. Seriously. Examiners love to mix these up just to trick you. So let's break it down. Your ailerons, they control roll. That roll happens around the longitudinal axis. Just picture a line running straight from the prop to the tail. And here's the kicker. Roll controls your lateral stability. That's a huge one. Next up, the elevator or stabilator controls pitch, which rotates around the lateral axis, a line from wingtip to wingtip, and that dictates your longitudinal stability. Finally, the rudder controls yaw around the vertical axis, which gives you directional stability. Knowing that ailerons control roll around the longitudinal axis for lateral stability is virtually a guaranteed point on your test. Memorize this.
And hey, real quick before we move on, you might see a question about how these surfaces are actually controlled. Now, most trainers use a traditional mechanical system, rods, cables, pulleys, physically connecting your yoke to the wing. But if a question pops up about modern upgrades, just remember that fly-by-wire literally just replaces those old-school mechanical linkages with an electrical interface. The computers step in to do the heavy lifting.
Moving right along to Section 2, roll and adverse yaw. Let's get into the physics of ailerons.
So to really grasp adverse yaw, we have to look at what the ailerons are actually doing out there on the wings. When you bank to the right, your left aileron goes down, right aileron goes up. That downward deflected aileron on the left increases the wing's camber, creating more lift to raise that side. But as we know, a byproduct of more lift is, more induced drag. So that left wing is lifting higher, but it's also dragging behind. This literally pulls the nose away from your intended turn. And that right there is adverse yaw. It's especially notorious at low airspeeds and high angles of attack.
Now, obviously, you can fix adverse yaw yourself by stepping on the rudder pedals, which, let's be honest, is exactly what your CFI is always yelling at you to do anyway. But over the years, engineers developed 4 distinct mechanical systems to counteract this effect automatically. For the exam, you need to know them: differential ailerons, Frise-type ailerons, coupled ailerons and rudder, and flaperons. Let's look at the 2 big ones.
First up, we've got differential ailerons. The concept here is incredibly clever, but honestly super simple. The mechanical linkage is designed so that when you turn the yoke, the aileron moving upward travels a way greater distance than the one moving downward. So the up aileron simply travels further, projecting right in the airflow to produce a massive increase in parasite drag on the descending wing. This extra drag totally balances out the induced drag over on the lifting wing, virtually wiping out that yawing tendency.
Now, what's really cool is the Frise-type aileron. Instead of just changing the distance the surface travels, it actually changes the pivot point using an offset hinge. When the aileron is deflected upward on the descending wing, its leading edge actually dips down below the wing's surface. It purposely shoves its blunt front edge right into the high-speed airstream. It acts like a mini speed brake, perfectly equalizing the drag across both wings. Oh, and bonus feature, it creates a little slot for air to flow smoothly over the lowered aileron, making it way more effective at high angles of attack. Win-win.
All right, Section 3, pitch perfect. We're talking elevators, T-tails, and stabilators. Most planes you're going to fly have a standard aft tail. Because an airplane's center of gravity is usually forward of its center of lift, the nose naturally wants to drop, right? So a conventional aft tail needs a constant downward aerodynamic force to act like a counterweight, pitching the nose up to keep you level. But you definitely might see a question about the canard design. A canard sits up front ahead of the main wing. Because it's up there, it actually creates upward lift to hold the nose up rather than pushing down. Theoretically, having 2 lifting surfaces makes the whole aircraft more efficient with less total drag. Pretty neat.
Now, if the horizontal stabilizer is mounted at the very top of the vertical fin, you've got yourself a T-tail. Watch out for these on your exam. While they're awesome at keeping the elevator out of the prop wash for a nice smooth ride, they have one major vulnerability: the dreaded deep stall. Because the elevator is up so high, flying at a high angle of attack paired with an aft CG can cause the turbulent wake off the stalled main wing to completely blanket the tail. If the tail is just sitting in dead, turbulent air, you lose elevator control. That makes stall recovery incredibly difficult, if not totally impossible.
To fight off those dangerous high AOA scenarios, especially in planes prone to deep stalls, engineers add a brilliantly simple safety feature, the elevator down spring. Say you're flying super slow, your aerodynamic trim tab loses its authority? Well, this spring automatically provides a mechanical load that physically pushes the elevator down to lower the nose. It's basically a built-in automated backup to prevent stalls when aerodynamic forces just aren't enough to push the nose over.
And that brings us to the stabilator, which you Piper pilots know all about. Instead of a fixed horizontal stabilizer with a hinged elevator stuck on the back, the stabilator is just one massive piece of metal pivoting on a central hinge. Because the whole tail surface pivots to catch the wind, it is wildly sensitive. So to keep the pilot from accidentally overstressing the airframe, it uses an anti-servo tab. You absolutely must remember this for the test. Unlike a normal trim tab, an anti-servo tab moves in the exact same direction as the stabilator. You pull back, the tab goes up, catching the wind and adding artificial heavy resistance to the yoke. It's there to stop you from over-controlling the plane.
Let's wrap things up with Section 4, yaw and V-tails, rudders and ruddervators.
Normally, we expect a vertical fin with a rudder for yaw and a horizontal fin with an elevator for pitch. But the V-tail, famously used on the Beechcraft Bonanza, combines your horizontal and vertical stabilizers into two slanted fixed surfaces. They form a perfect V-shape and handle both directional and longitudinal stability all at once.
So how on earth do you control it? The movable parts on the trailing edge are cleverly called ruddervators. Because there are only two surfaces handling both pitch and yaw, they rely on a super complex control mixing mechanism hidden away in the tail. When you pull the yoke back, both ruddervators move up equally to pitch the nose up. But if you step on the right rudder pedal, the mechanism moves the right ruddervator up and the left one down to yaw the aircraft. It is a really fascinating mechanical translation of your inputs.
But definitely be careful here. V-tails come with some caveats for your exam. While they look incredibly sleek and futuristic, they actually don't reduce total drag all that much compared to a conventional tail. Plus, that complex control mixing mechanism we just talked about, it adds a lot of maintenance, weight, and complexity. And aerodynamically, they make the aircraft much more susceptible to Dutch roll tendencies, which is this really uncomfortable combination of rolling and yawing. Make sure you memorize those three disadvantages.
Okay, I know that was an absolute fire hose of aerodynamics and mechanical systems, but you now have the exact, structured knowledge required to completely crush this section of your written test. You know the axis, you know exactly how to combat adverse yaw, and you understand the quirks of every major tail configuration.
Actually, speaking of rotating around axes, why did the airplane break up with the helicopter? Honestly, it was just tired of the constant rotating.
Okay. Dad jokes aside, I really hope this clarified the wild world of flight controls for you. The key takeaway is to trust your study routine and remember the mechanics we just broke down. But before you log off, I want you to think about this. As fly-by-wire technology and automated flight control systems become the standard, even in small GA aircraft, will traditional mechanical setups, like offset hinges and downsprings, eventually just become obsolete relics of the past? Let me know what you think down in the comments. Good luck, go ace that ground exam, and please make sure to like and subscribe for more deep dive cram session explainers. See you in the skies.